Okay, we are off to chapter 12 here. We finished up chapter 11 last time, talking about electron configuration, all that good stuff. We also talked about periodic trends as well. So in chapter 12 here, we're going to officially talk about bonding, different types of bonding that we're going to come across. There's really two types of bonding that we come across. One is ionic bonding. And in ionic bonding, it is always a metal and a non-metal that comes together. And really, because of those periodic trends that we talked about, metals again have all the trends that they want to get rid of their electrons and lose them. Non-metals have all the trend where they want to really accept them. In this case, we end up getting a transfer of electrons that occur between the metal and the non-metal. The metal results in a cation formation that is positively charged. The non-metal results in an anion formation that's negatively charged. And one of the important things to remember in ionic bonding is there is no sharing of electrons that's occurring. So we do have a transfer of electrons. It is held together by the electrostatic attraction. The other type of bonding we're going to talk about is one's a molecular bonding, which is really a covalent bond. And in a covalent bond, that is between two nonmetals. And because they are two nonmetals involved in this type of bond, they are located in a similar spot on the periodic table, which means they both share basically similar periodic trends. Neither one of them wants to get rid of their electrons. So the best that they will do is, because they want to hold on to their electrons, they actually want to gain electrons. They will actually share electrons here. So that's a major difference between them. We get some sharing of electrons. The sharing will be either equal sharing or unequal sharing. But as we'll talk about in this chapter, there is some aspect of sharing that's going on here between those two. So that's really a dramatic sort of difference between the two. Metal, non-metal, ionic, transfer of electrons, no sharing of electrons. In a covalent bond, we do have nothing but sharing of electrons, which could be equal or unequal. So one of the ways that we represent sort of bonding, both ionic bonding and covalent bonding, is to use Lewis dot symbols. They're nowadays just generically called electron dot symbols. And basically we use them to help us understand what's going on with bonding. When we talk about bonding, there's really only a certain type of electrons that are involved, and those are our valence electrons. So our valence electrons are, again, really the only electrons that are involved. They are the highest, most energy electrons. A reminder that you can very easily figure out the valence electrons as it equals basically the group number on the periodic table. So everybody in group 1 has one valence electron. Everybody in group 2 has two. 3, 4, 5, 6, 7, and 8. Again, you could also write the electron configuration and figure out how many valence electrons things have. The one exception for that is actually helium. So helium is a member of group 8, but it only has two total electrons. So it only has two valence electrons because it doesn't have 8 electrons. So everybody else in group 8 will have 8 valence electrons. We basically use this symbol and one dot to represent each of the valence electrons that are present. There's really no kind of rule per se. The only rule is we usually don't go more than 2 per side. And since there's 4 sides there, that is a total of 8, which once again puts everybody into that noble gas configuration. As we'll talk about, that really is the whole point of all types of bonding, is for everybody to achieve the same electron configuration as our noble gases. That makes it really, really stable. Here again is a picture of some Lewis dot symbols. You can see everybody in group 1 has 1, everybody in group 5. Again with helium. This is also why, for example, everybody wants to be like a noble gas in terms of bonding or in terms of electron needs to, because it just needs to get to helium, and that's why hydrogen should never. say that like hydrogen with 4 million electrons and bonds and stuff like that. Pretty much what I just drew there in the middle is what hydrogen should always look like when you draw it, pretty much just like that. It can never have more than 2. Everybody else needs 8 to get basically over here to our noble gases, which are stable. But again, hydrogen just needs to get over there to helium to be stable. Now, again, as we talked about, there are elements that are ionic, always a metal and a non-metal. Pretty much, if you have that combination happening, it should be really a no-brainer there. It should always be ionic. That's pretty much all you need to see is a metal and a non-metal together, and you'll have an ionic bond. Covalent compounds, again, are going to be our nonmetals together. So our non-metal combination is basically what's going to make that. And typically speaking, things with low ionization energy will typically form positively charged ions. That, again, is to the left and down on the periodic table. Those are metals, low ionization energy. Again, ionization energy, the energy required to remove an electron. So if you have low ionization energy, it means it's super easy to remove an electron. As opposed to if you have high ionization energy, then you are very hard to remove an electron. Things with high electron affinity tend to form anions. Electron affinity is the energy change that occurs when somebody gains an electron. So if you have a high negative electron affinity, that means you're pretty darn good at accepting electrons. And those are typically what we find in our nonmetals up and to the right on the periodic table. It increases along with things like electronegativity. So general rule tells us basically to the left there, metals are going to be positively charged, and non-metals there, an oxygen will be negatively charged. So let's take a look at an example here of lithium fluoride. And again, when you're trying to determine what you're dealing with, really you should think about what types of elements you have going on here. So lithium is a metal. Fluorine or fluoride is a nonmetal. And again, with that combination, that should tell you here that this is going to be ionic, and we're not going to get a sharing of electrons. We're actually going to get a transfer of electrons that's going to happen. So lithium is group 1, which means lithium does have 1 valence electron. And if we write the electron configuration for it, 1s2, 2s1, right here, so I mess it up there. Right there is the 1 valence electron, and that is its valence electron. Remember that lower energy electrons are referred to as core electrons. They are not involved because they're really close to the nucleus and they're held really, really tightly. It is just those outer valence electrons that are involved. We have our fluorine, which is group 7, which means it does have 7 valence electrons. Looks something like this. A little 1s2, 2s2, and 2p5, I believe. Right here is the 7 valence electrons there in fluorine. So because of those periodic trends that we talked about, pretty much our lithium's going to go take my electron, and the fluorine is going to go, thank you very much, I will. And we're going to get that transfer of electrons over. The result of that is it's actually going to form our ionic bond. Our lithium will now become +1 as it has lost an electron and now has more protons than electrons. And our fluorine in this case will become fluoride. It will gain 1 electron. And as a result of that, it now becomes negatively 1 charged. And we'll have a -1 charge in this particular case. That is going to form our ionic compound and our ionic bond between those two. Once again, there is no sharing of electrons here, just a transfer of electrons from the lithium to the fluorine in this case. And that attractive force between the positive and negative charged ion here is what holds that together. Now, typically when you draw something like this using Lewis dot symbols for ionic compounds, you should put brackets around at least one of them. And you should also indicate the charges there. And those charges indicate that those electrons are not being shared, that they have been transferred as well. So you should include the charges and some brackets there. Now, in terms of what's happening here, if we think about it, our lithium has basically given away its one valence electron. That means that our lithium now ends up with only 2 electrons, which means its electron configuration is 1s2. And 2 on the periodic table there, as we just talked about, is our friend helium's configuration. The fluorine had a spot open in that p subshell for that electron that came over, and it now will have 10 electrons, 1s2, 2s2, 2p6, and 10 on the periodic table is neon's configuration. That right there is basically the goal of all bonding, is by, in this case, the metal losing electrons, the nonmetal accepting electrons. They both are able to achieve that noble gas configuration just like the noble gases. And that's a really, really stable configuration. That's really, again, the whole purpose of doing so. First off, any questions on that there? The way that metals and nonmetals do that is through the transfer of electrons. If you look at the periodic table, you will see, again, lithium backs up to the noble gas that comes right before it. The nonmetal, which accepts the electron, actually goes forward on the periodic table to the noble gas that comes after it. They both achieve that really stable configuration, and that is what makes pretty much our ionic bond in this case. Any questions on that there? So let's take a look here, maybe at another one. So as I mentioned a second ago, what holds that together is the opposite attraction between those ions, and that is an ionic bond, no sharing of electrons between those two things. Let's take a look at calcium oxide. If we look at calcium, calcium is group number 2. It has 2 valence electrons, and if we write the electron configuration for calcium, it is argon 4s2. Again, these 4s electrons here are valence electrons. Our oxygen is group 6, so 2, 4, 5, and 6 here. And it has an electron configuration of 1s2, 2s2, 2p4 in this case. Once again, when these two get together, our calcium is going to want to get rid of its electrons. So it's going to send over to our oxygen an electron. Good news here is it could actually send both of those electrons over to the oxygen, as it has room for it right there in this p subshell, basically. The result of that is the calcium at that point, by losing both electrons, will end up with a +2 charge. The oxygen will actually gain 2 electrons, and it's at that point it becomes a -2 charge. And once again, no sharing of electron, but that attraction between those two charges is what's holding that together. Once again, if we look what happens in terms of the electron configuration, calcium started at 20 electrons, gives away these 2 valence electrons, ends up at 18 electrons, and achieves argon's configuration. As I mentioned earlier, the oxygen has room right there in the p subshell, which could hold 6 electrons total. Takes in those 2 electrons, ends up at 1s2, 2s2, 2p6. That is our 10 electrons, and ends up at neon's configuration. So once again, in this particular case, both of these guys achieve noble gas configuration by transferring electrons from the metal to the nonmetal. Questions on that there? Does calcium and oxygen become argon and neon? They do not. So a reminder that what we're talking about here is they just end up with the same electron configuration as the noble gases. Remember, it's the protons that are most important. So we don't touch anything with the protons here. So they don't change. So they're still calcium and oxygen, but they just have a much better electron configuration than they started with in this case. Any questions on that there? So in this case, we have the charges again also shown. So what happens if we actually kind of combo both of these together that we saw before? If we take a little calcium, which has 2 valence electrons, and we put it together with fluorine, which has our 7 valence electrons. In this case, we are going to get the same situation. We're going to get our electrons being transferred. So here, calcium will give away an electron. At this point, though, can that fluorine take any more electrons? No, because it's full, right? It's at only really one spot open there for our electron there in the p subshell. That's also problematic for calcium because if it only gives away one electron, if you look on the periodic table, it's just going to back up to potassium, which is not a noble gas. So that's not going to achieve what it needs to become stable. So in this case, we actually don't need just one fluorine. We actually need a second fluorine. And this second fluorine now also has a spot that can accept the case. The result of this is we will now end up with a calcium that has a +2 charge. We have one fluorine that gained one electron only. And because it gained just one electron, it becomes -1 charge. We have a second fluorine, which also gained just one electron and ends up with a -1 charge. And again, what holds this all together is the attractive force between all those guys. Once again, no sharing of electrons. If we look at what happens with our electron configuration, by giving away an electron to each of the fluorines, calcium was able to give away a total of 2 electrons, again getting calcium to argon's configuration. Each of the fluorines picks up 1 electron here, which gives it a total of 10 electrons. So both of these fluorines able to get to neon's configuration and be stable. This is why when we talked earlier in that chapter about balancing out charges on ions, when we take something like calcium that has a +2 charge and fluoride that has a -1 charge, this is the real reason why we need 2 of them to balance out the charge. -2 + 2 gives us our proper formula here of calcium fluoride. So really the reason why we try to balance it out to 0 is to get everybody into that really stable noble gas configuration in the simplest way possible. Yeah, I really wouldn't want to do that. It's not very stable. So the idea really of all bonding is to make things more stable. And a lot of times there's a lot of energy component with bonding as well. So overall, when we do like ionic bonding or even when we do covalent bonding, there's sort of a reduction in the overall energy of everything, which allows it to stay together, right? Because everything has energy even when they come together, right? So if you got something that's really not so stable, they're going to be bouncing around a lot. They're not going to be able to kind of maintain themselves. And that's why we want to get it together in the simplest way possible to do so. Yeah. And that's really the reason, like I said earlier, that we balance out the charges when we're doing ionic formulas is for this reason. It's really the bonding reason. And by doing it in the simplest way to get it to 0, obviously in this case, we could do like, 2 calciums and like 4 fluorides, right? And that gets us to 0. But that's not going to create really the stable bond that we need. We need it in the simplest way possible to get to 0. And that allows everybody there basically to get to that stable configuration. Other questions? Yeah. So what we're seeing here is how you should represent, obviously, ionic bonding. We don't use lines or anything like that because there is really no bonds happening here. There's no sharing of electrons. And again, that's why we also need to indicate the charges when we draw these type of sort of compounds. Any questions on that? All right, there. Now, covalent bonding is different in the sense of what's going on. Now, as I mentioned before, covalent bonding is when you got those 2 nonmetals coming together. And once again, because they are both nonmetals, they both are pretty much not going to give up their electrons. So they will agree to sort of share them, as we'll talk about shortly here. Again, either it's going to equal share or unequal sharing. makes that sort of situation. So Gilbert Lewis suggested a role of bond formation here by sharing of electrons, hence why we call them Lewis structures, I'm assuming. And basically, if you took something like hydrogen, for example, here, which has one valence electron, and another hydrogen that has one valence electron, what's going to happen is, in this case, they're both hydrogen. They both basically have the same electronegativity that's going on. And they're not going to transfer their electrons. They're just going to decide to share those electrons. And what's going to happen in this case is we will end up with an actual bond that's happening between the two hydrogens, where the electrons in the middle will count for the hydrogen on the left. And by sharing those electrons, they will also count for the hydrogen on the right. In this case, essentially, our friend hydrogen, as we talked about, each of them end up with 2 electrons, which, as we talked about, is pretty much all hydrogen should have, as it just needs to get to that neon, which is 2. I'm sorry, the helium, which is 2 on the periodic table there. And that will create a bond. You could represent a covalent, the sharing of those electrons, as either a line, which represents the bond, or you could use dots. I would say most of the time use lines to represent bonding electrons and bonds being made, but dots are not incorrect per se, but most of the time people use lines. By the way, that is what's referred to as a single bond, which shares basically a pair of electrons. We could also have double bond, which are 2 lines, represents, again, 4 total electrons or 2 pairs. And we could have a triple bond, which is just 3 lines, which basically represents 6 total electrons, are 3 pairs of electrons. Now, again, sometimes what is holding these electrons between these 2 atoms is the attraction to the nucleus, right? Nucleus is positively charged, electrons are negatively charged. So they're between the 2 atoms. So the attraction to one nucleus and the attraction to the other nucleus sort of locks everybody into place in terms of the electrons between the 2 atoms in that particular case, and you do get a bond that occurs. Now let's take a look at fluorine. So in this case here, we have fluorine, which is group 7, has 7 valence electrons. And once again, we have another fluorine, which has 7 valence electrons. Clearly here, they both have the identical periodic properties and electronegativities. So they're going to decide to share those electrons. The result of that, again, is we're going to end up with a bond being formed here between the 2 fluorines, which you can represent, again, as all dots. Or for that one where the bond is, you could use a line to represent that. And once again, in this case, by the fluorine on the left there, sharing those electrons, it ends up with 8 electrons. Sharing those electrons in the middle for the guy on the right also ends up with 8 electrons. So in this case, by sharing electrons, everybody achieves that kind of noble gas configuration and is really happy for that. Any questions on that there? Now, when we look at a picture like this that we saw in fluorine, there are different types of electrons that we sometimes come across. All these electrons are represented with dots that are not involved in bonding. And once again, I know they're not involved in bonding because there's frankly nothing on the other side of those dots. So I know there's no bond being made. Those are what are referred to as non-bonding electrons, people like to call them these days. If you're old like me, I suppose lone pairs, you'll probably hear me say. So lone pairs, non-bonding electrons are the same deal. They basically are the ones that are not involved in bonding. That also leaves us, obviously, the electrons there in the middle, which right here are involved in bonding, and they obviously have a much creative name of known as bonding electrons. So bonding electrons, much like the name implies, are electrons that are involved in a bond. Non-bonding or lone pairs are not involved in bond formation. You should always, when you draw Lewis structures, should always include all those electrons. All the non-bonding electrons and the bonding electrons should always be shown. Non-bonding electrons should always be shown as dots, unless maybe you're taking organic class later down the road. Maybe they'll sometimes show them as lines. Don't do that in general chemistry usually. We do show them as dots or pairs of dots. So a Lewis structure, as I said before, is a really representation of bonding, both ionic bonding and covalent bonding. And again, remember that we're only showing the valence electrons. Obviously, each of these elements have the core electrons still available to them. But again, they are not involved in bonding, so we don't represent them in these type of structures. Another example of this sort of covalent bonding is what we see here in water. Water actually, by sharing with in water the oxygen and hydrogen, the hydrogen there gets 2 electrons. Hydrogen on the left will get 2 electrons by sharing with the oxygen, and the oxygen actually sharing with both of those hydrogens will end up getting 8 electrons. Once again, that's just moving everybody to that noble gas configuration, making a really stable bond to occur in this particular case. So clearly we've been talking about, but officially, right, the number 8 is kind of important in bonding. That is what is known as the octet rule. Basically, it states that everybody will continue to make bonds until they have 8 valence electrons around them, except for obviously hydrogen, as we mentioned a number of times. Once again, hydrogen only needs to, sometimes referred to as the duet rule. So once again, hydrogen always should look like that. If you find yourself like triple bonding hydrogen and also putting dots on it for good measure, you're going to get a big X. Yes, that is definitely wrong for sure. Shouldn't probably have any dots on it unless you're not using lines to represent a bond. So if you're using dots, you can use that. Otherwise, it should not have any for sure on it. So we talked about it a second ago, multiple bonds. Now, to get everybody to the octet rule, sometimes all you need is a single bond, and a single bond will get you there, and that will allow everybody to achieve that octet rule. As we see in fluorine, once again, one line are 2 dots there to represent a single bond. Now, in certain cases, you actually need a double bond, for example, to get people to the octet rule. Carbon dioxide is an example of that. Here, the oxygen, by sharing with the carbon, gets to 8 electrons. Same thing with this one. And the carbon, by sharing with both of the oxygens, actually gets to 8 electrons. In the case of carbon dioxide, you actually need a double bond on both sides to allow everybody there to get to basically 8 valence electrons. A double bond, once again, represented either by 2 lines or 2 pairs of electrons, or 4 total electrons when it's all said and done. And obviously, sometimes it does take a triple bond to get you there. And nitrogen, for example, is an example of that. Triple bond is 3 lines, are once again 6 total electrons, are 3 pairs of electrons basically here. Now, a very common mistake that people make when they go to draw Lewis structures, as we'll do here in a bit, is they oftentimes want to like double bond and triple bond right out of the box, and always a bad idea to do that. So usually you want to stick with single bonds until it is necessary to kind of double bond or triple bond. So what makes it sort of necessary in most cases is somebody has not met the octet rule through basically single bonding. And you should think of using double bonds and triple bonds as sort of to try to fix that problem. And you actually kind of go in that order, usually will get you the right sort of picture. You want to double bond first, and if that doesn't fix the problem, then you want to go to a triple bond. So usually when you're drawing Lewis structures, that's sort of the order you want to think about. Single bond first, doesn't fix it, double bond, exhaust all your double bond opportunities. And then if that doesn't fix it, triple bond is where you want to go next. Again, you typically do not want to double bond or triple bond out of the box. It usually does not give you the best structure a lot of times if you do that. Also, as we'll talk about when you're drawing some of these things, you want to think of the electrons as not necessarily belonging to one element or another in a covalent situation, as to more so you want to kind of distribute everything a little bit more equally. Now, when we do have sharing of electrons in terms of covalent bonding, how do we know how those electrons are going to be shared? Electronegativity really is the overwhelmingly thing that you should look at. And a reminder on the periodic table, electronegativity increases as you go this way up and to the right. Fluorine is the most electronegative you could have, and it decreases as you go down. Electronegativity is that, again, ability of an atom to bring electrons towards itself. And it really is electronegativity that we look at when we're trying to determine just that, like I said, how those electrons are going to be shared. As we will see, you can also use electronegativity to figure out whether or not you would expect an ionic bond, but truthfully, you don't really need it for that, because if you have a metal and a non-metal, you should know it's ionic. So really, we look at electronegativity to help us figure out, basically, within a bond between two nonmetals, will they share those electrons equally or unequally? So let's talk a little bit about that. So if we had something like hydrogen, for example, and we have our hydrogen here sharing our electrons, and in this case, what's going to happen is, because these electrons in hydrogen, they are both hydrogen, the electrons are actually going to be shared equally. They're going to be pulled by the hydrogen center kind of the same. So if this red is sort of the electron density and sort of how it's being shared, it will be shared really equally between them. And what that means is, ultimately, this type of bond where you have sort of equal sharing of electrons is known as a nonpolar covalent bond. I would say probably 9 out of 10 people would just simply call it a nonpolar bond. It is covalent, but it's sort of implied in most cases that we're talking about sharing of electrons here. So if you hear somebody say a nonpolar bond or a nonpolar covalent bond, they're basically talking about the same thing in this case, equal sharing of electrons. The consequence of this type of sharing is you create, for the lack of a better description, a neutral bond. There is no like positive side, negative side. It's like perfectly balanced in terms of the charge of that bond between those two things. And that's sort of what a nonpolar bond is. Now, what happens when we have something like HF? We take out one of those hydrogens and exchange it for a fluorine. Now what we have is definitely a difference in electronegativity between the two atoms here. And between hydrogen and fluorine, the more electronegative is which one? Hydrogen or fluorine? It should be fluorine. It is the most electronegative. So when these guys share electrons, what's going to happen is the fluorine is like, I'm just going to take most of those if you don't mind. And we're going to get really unequal sharing. So if this blue line is like my electrons, for the most part, most of the electrons will then head towards the actual fluorine in this bond. The result of that is, because most of the electrons are actually heading towards the fluorine side, it will create a partially negative charge, delta negative or partial negative charge on the fluorine. It will create a partially positive charge on the hydrogen part of this bond. And that's because the electrons are heading towards the fluorine, and they're hanging out closer to the fluorine than they are the hydrogen in this bond. You could also represent this by an arrow, which is sometimes referred to as a dipole arrow. That is pointing towards the more electronegative side. And the back part of the arrow that makes like a plus sign is actually to the more positive side, or the less electronegative side in it. This is what is sometimes referred to as a dipole arrow. And different than what we have in a nonpolar bond, when we have kind of a neutral bond, because of the difference in electronegativity here, and because of the unequal sharing, we actually get a bond that has actually charges on either end. There's a more positive side to that bond and a more negative side to that bond. Any questions on that? This is what is referred to as a polar covalent bond, or what most people just refer to as a polar bond. Again, it is covalent. Why is it in this case that I end up with, on this guy here, a partially negative charge and a partially positive charge? Why do I not get a full positive charge and a full negative charge in this case? Like I do, say, in an ionic bond, where we have it. Yeah. That's absolutely the answer. Yeah. So in this particular case, because there's still some aspect of sharing, it is only a partially negative charge and a partially positive charge because they're still hanging on. It's like tug of war, right? One guy's pulling the rope really strong and somebody's just barely hanging on, getting dragged around the ground there. Still hanging on, right? But not so well. But there's still some aspect of sharing. In ionic compounds, we get a completely full transfer of electrons from the metal to the non-metal. So there is no sharing that occurs, a complete transfer. So whoever loses the complete electron becomes more positive, and whoever gains the electron becomes more negative. So that is absolutely the reason there. Any questions on that there? All right, so as I said before, that is a polar covalent bond, or just a polar bond, unequal sharing of electrons, more of a charged sort of situation occurring. And again, like I said, you can use that arrow sometimes to represent that. And that, again, is what is sometimes referred to as sort of bond polarity. And that's what we're talking about in a lot of cases when we're talking about, again, just how the electrons are being shared between two atoms. That is sometimes referred to as bond polarity. That is not molecular polarity in all cases. Sometimes it is the same, but molecular polarity is the entire molecule as a whole. All the bonds involved, are they sharing the electrons equally or unequally? So you could think of the three types of bonding that we talked about as, on one end of the extreme, we do have ionic bonding, and that is always a metal and a non-metal. So once again, that is pretty much how you could identify it as being ionic. Because of those differences, as we talked about, we get the transfer of electrons resulted in our cation that's positive, our anion that's negative. And again, opposite attraction there. No sharing of electrons here, like in sodium chloride. On the other end of the extreme, we have a nonpolar covalent bond. And that is between two nonmetals. And that is where we have equal sharing of electrons. And an example of that is like our H2, our F2 as well. Now, when you have a sharing of electrons that is like perfect equal sharing of electrons, sometimes people refer to that as a pure covalent bond. And a pure covalent bond is when you got like the perfectly as equal sharing of electrons as possible between two atoms. It is still a nonpolar bond, but sometimes people will classify that perfect equal sharing of electrons as a pure covalent bond. In the middle of those two, we have our polar covalent bond. And that is where we have, again, two nonmetals. We have unequal sharing of electrons. And again, that's going to produce an example like that there, where we will get some charge happening here on each side of that bond. So one end of the extreme with ionic, complete transfer. Other end of the extreme, perfect sharing of electrons. In the middle, not so unequal sharing that they transfer, but not equal sharing that they're perfectly equal with each other. So some degree of unequalness in terms of the sharing. Any questions on any of those types of bonds there? No. So how does electronegativity help us really decide that? We're going to talk about how we can use electronegativity to really help us determine, what type of bond should we be dealing with? Again, electronegativity is that ability to bring electrons towards itself, an atom. It's based on electron affinity, which again is the energy change when somebody gains electrons, and ionization energy, which is the energy required to remove electrons. Fluorine has high electron affinity, likes to gain electrons, and high ionization energy, doesn't like to lose electrons, and it has high electronegativity. Sodium, on the other hand, has low electron affinity, doesn't like to gain electrons, and has low ionization energy, which means it doesn't like to hold on to its electrons. So it typically will give away its electrons, become positive, and has a low electronegativity. Now, Pauling actually came up with a scale for electronegativity. Pauling's scale runs from 0 to 4. 4 is the most electronegative. 0, not so much, right? So we actually could use the difference in electronegativity values, which we'll see here on a table in just a second, to help us calculate what type of bond we would expect to occur. So you could calculate what is sometimes referred to as delta En, delta meaning change, En meaning electronegativity. So that's the change in electronegativity. You basically take the two values in the bond, one for each element that's in the bond, and you basically just subtract the larger from the smaller so you get a positive number. And if you do that and you end up anywhere from 0 to 0.4, that is considered a nonpolar bond. So if you got 0 to 0.4 difference, you could consider that nonpolar. You could consider that equal sharing of electrons, basically. If you're above 0.4, which is like 0.5, to less than 2, that's going to result in a polar bond, unequal sharing of electrons. And typically above 2, a usual result in an ionic bond, no sharing of electrons. So earlier I said you really don't need electronegativity values for ionic, and it still holds. If you got metal, non-metal, don't even worry about the numbers. It should be ionic. We really will oftentimes use difference in electronegativity values to help us with covalent bonding, sharing of electrons, and again, we want to see are they going to be shared equally or unequally. I talked about a pure covalent bond a second ago, and how you get a pure covalent bond is a lot of times your difference in electronegativity is 0. That's like perfect equal sharing. As you can see, you could go upwards of 0.4 and still be considered equal sharing of electrons. In reality, if you were around 0.4, is it perfectly equal sharing of electrons? It is not, right? There's a slight difference, but not enough to be considered unequal sharing of electrons. So 0 difference basically is pure covalent, nonpolar, as equal of sharing of electrons as you could do. Here is a table of electronegativity values, which obviously the values would be provided for you if you needed them. You just need to know what to do with them. So for example, we take some of the ones that we did earlier or talked about, NaCl. We'll do F2. And we'll do HF in this case, right? So if we wanted to use this table, this is basically what we would do. We would find the two elements that are involved. So we'll start over here with our fluorine. So fluorine is 4. So this guy has a value of 4. This one has a value of 4. When I do the difference in electronegativity, that is 4 minus 4, which is 0. And that is obviously between 0 and 0.4. That tells me that this should be a nonpolar bond. It could also be labeled a pure covalent bond because the difference is 0 as well, which is a nonpolar bond in this case. If I go here for hydrogen, hydrogen is 2.1. Fluorine is 4. Once again, just going to take the larger number minus the smaller here. So difference in electronegativity, 4 minus 2.1, going to give me 1.9. 1.9 difference is above 0.4, less than 2. So that falls in the polar range. And this would be a polar covalent bond. Again, we could draw that arrow as we did earlier, pointing to the one that is more electronegative, which in this case would be fluorine. If I come over here to sodium chloride, sodium is 0.9, chlorine there is 3. So taking the difference in electronegativity here, we got 3 minus 0.9, 2.1. That is above 2, which tells me it's ionic. Once again, I really don't need the numbers because I know that's a metal and a non-metal, so I know it's going to be ionic. So you really don't necessarily need the numbers per se for ionic. Question on how to do that there. All right, so why don't you try some here? Let's see. For each of these bonds, is it ionic, polar, or non-polar? Let's do the bond between carbon and oxygen. Let's do the bond between sulfur and oxygen. Let's do the bond between carbon and hydrogen. Let's do a little potassium. We'll do potassium chloride. Let's do the bond between nitrogen and chlorine. All right, so calculate the difference in electronegativity for each of these and determine is it polar, non-polar, or ionic in this case. Okay, so let's see how you're doing. So once again, we're just going to find the two numbers here, basically subtract them. So we'll go carbon, which is 2.5 on the table there. Oxygen is 3.5. So here again, if we do our difference in electronegativity for that guy, 3.5 minus 2.5, that is going to give us a 1 difference. And again, that is above 0.4, but less than 2, which tells us that this bond should be polar because of that. We should draw the arrow pointing to the more electronegative oxygen in this case. And it should look something like that if it wasn't scrambled up on the top there. Any question on that one there? We take our sulfur here. Our sulfur is 2.5. So I'll borrow that for sulfur as well, 2.5. Our oxygen is 3.5 in this case. And in this case here, we end up with a difference in electronegativity of basically the same thing there. We will end up with a polar bond, a difference of 1 when we subtract it, as was the same numbers in this particular case. Again, the arrow should point towards the oxygen, which is more polar. And again, making a polar bond. We take a look at carbon and hydrogen in this case. Carbon is 2.5. Hydrogen is 2.1. So the difference in electronegativity, 2.5 minus 2.1, that is 0.4. 0.4 is the cutoff for nonpolar. This would be a nonpolar bond. The reason for that is it's organic, and organic molecules are nonpolar, which is why the cutoff goes to 0.4 to cover the carbon-hydrogen bond, basically. And this would be a neutral bond. You would not draw any arrows on anything that's nonpolar, again, because there's no separation of charge, so there would be no arrow drawn in this particular case. Yeah. Any questions on that one there? Looking at potassium, potassium is 0.8, I think it says. And our chlorine that we saw there is 3. So once again, if we did the difference in electronegativity, you could take 3 minus 0.8. That looks like a 2.2 perhaps. And that definitely is above 2, and it's ionic. Once again, you don't really need it because that's a metal, non-metal, and you should know it. I say that because there is definitely places where you can take a metal value and a non-metal value together, you can listen to the electronegativity values and just use it really more for covalent bonding in that case. Lastly, here we have nitrogen, which is 3. And we have chlorine, which is 3. So the difference in electronegativity in this case is 3 minus 3, which is 0. That makes this guy a nonpolar bond. Also makes it a pure covalent bond. as well, which is nonpolar. This is a good explanation that, or example that you can have two different elements that actually share the same electronegativity values and will be a nonpolar bond. The reason for that, if you look on the periodic table between nitrogen and chlorine, they are what are referred to as having a diagonal relationship with each other. One is further to the right, one is further up. They cancel out their differences. It's not like right below it diagonal, it's kind of down and to the right one. Same thing here. If you look at carbon and sulfur, diagonal relationship that occurs there, they have the same electronegativity value. So it is absolutely possible to have two guys that have the same electronegativity value that are different elements. Question on that there. Definitely, if they are two of the same element, then clearly it's going to be a nonpolar bond. They're going to share it equally. Now, do you need, for example, the values to make a reasonable guess on electronegativity? The answer is you really don't. As long as you know the general trend in electronegativity, you can make a pretty good assumption, especially if you're comparing two elements that are in the same row or same group on the periodic table. So for example, take our carbon-oxygen bond. That's carbon, that's oxygen. Oxygen in the same row as carbon further to the right, which means it should be negative, and it should give you a polar bond without even using the numbers. So the same row, that should give you enough of a difference that you should end up with a polar bond. Same thing if you looked at sulfur and oxygen, they're in the same group, and oxygen is further up in the group, which means oxygen again should be more electronegative, and because they're in the same group, you should know that it should be a polar bond. So if you're comparing two elements within the same group or the same period, it most likely will yield you a polar bond if they are not in the exact same square, which they won't be. And the one that's further to the right or further up will be the more electronegative atom, and that's where the arrow should point in this direction, or that case. Any questions on that there? What we are looking at here is what I said before. This is when you use difference in electronegativity values, you typically are looking at bond polarity, is sometimes referred to. Bond polarity is simply just between the two atoms within that one bond by itself. Are they going to share the electrons equally or unequally? There are cases where it will be the same as molecular polarity, but in most cases, it will not be unless it's a diatomic molecule. If it's not a diatomic molecule, then it will not be the same thing, basically. If it is, it actually will be the same thing. But usually when we use difference in electronegativity values, we're looking at bond polarity. Question on that there. All right, so as we saw there, atoms with widely different electronegativities tend to form ionic bonds. Those that are similar will form covalent bonds. Again, up to the right, our nonmetals are in the same location, going to share those electrons. You get a metal and a nonmetal left and right side of the periodic table, going to get that difference and transfer of electrons that is going to occur. So our ionic bond, as we've been talking about, are basically those two things. And really, when you have this guy here, you know it's ionic. When you have two nonmetals, you know it's covalent. And really, at that point for covalent, what you have to decide is, are they going to share them equally or unequally? It's basically the two things you want to think about when you look at a covalent bond. So as I mentioned a second ago, that sort of 2 value for ionic is not perfect. And again, there is a number of examples. You could take the difference and you'll be less than 2, but it's still ionic. So use what we just talked about there. I would say a lot of people don't talk too much about percent ionic character, but sometimes people will classify bonds based on percent ionic character. If you have 100% ionic character, you pretty much have an ionic bond. And if you got 0% ionic character, you pretty much have a pure covalent bond. And if you have a percentage kind of in between those two numbers, you most likely have some type of polar bond happening. So I would say not too many people kind of use the percent ionic character, but that's essentially the same idea as what we just talked about with ionic, polar, and nonpolar bonds, basically. So you sometimes will see that. Here again, Equal sharing, pure covalent, nonpolar bond. Unequal sharing of electrons, polar bond, more electronegative heading that way. Ionic bonding happening over here in this case. Again, this would be more 100% ionic character. This would be 0% ionic character on that side of it. And again, obviously our polar guy in between that. So let's talk then about drawing actual Lewis structures for covalent compounds. And again, what we're going to be talking about here is really the steps that you should follow, and it will get you hopefully to the right picture when it's all said and done. Again, if you don't follow this, guys, you oftentimes will end up with too many electrons, not enough electrons, too many bonds, all that stuff happening. The first thing you want to think of when we're talking about covalent bonding and drawing Lewis structures is this. Obviously, we want to think about how everybody is arranged. And to help you decide where everybody should be in terms of bonded together is the least electronegative atom should find itself in the center. So usually the least electronegative is in the center. That means the fluorine should never be there because it's the most electronegative. That also means hydrogen should never be in the middle because if you put hydrogen in the middle, it's going to have more than 2 electrons. So you can never put it there. So it always should be on the outside in that case. Now, once you have sort of the logical arrangement, and I would say probably most of the stuff that you guys will be drawing in this class and maybe even the next class will most likely only have like one center atom and everything attached to it. It is definitely possible to have multiple center atoms and things attached kind of weirdly. But most of the time for us, it would probably be one thing in the middle and everybody else is probably attached to the guy in the middle, but it can be a little bit different than that. You want to count the total number of valence electrons, and this number is really important because when you're done with your picture, you got to have exactly that number of electrons in your picture for it to be correct. Remember again that the electrons, valence electrons equals the group number, so that is the way we can calculate that. Come across something that's a polyatomic ion or an ion in general, and polyatomic ions are actually weird things that are nonmetals that are actually sharing electrons, but because of the way they're sharing electrons and who they're sharing electrons with, they actually end up with such unequal sharing that they end up with charges. They actually have an overall charge like an ion. So it's like a combo of covalent bonding, but actually it's an ion, like it works like an ionic bonding when it hooks up with somebody. Now, if somebody has a negative charge, we want to add that number to the total because they gained electrons. If somebody has a positive, get rid of that there and make that positive. If somebody has a positive charge, that means that they have lost electrons, and we should subtract that from the total. So if something has a charge, you do need to adjust the overall count. Otherwise, you will end up with too many electrons, not enough electrons in that particular case. Now, the valence electrons is the exact number that you need when you are in your picture. It is also what I was talking about before that, you don't want to think about it like, hydrogen has 1, nitrogen's got 5, and try to figure out kind of like what we do with ionic bonding, how the electrons come together. In covalent bonding, you usually will end up screwing it up pretty good. You want to think of these electrons as not really belonging to anybody, but sort of you want to distribute them as equally as possible over everybody to get everybody to a stable situation. And that's the best way to think about it. How do we do that? Once we have sort of the arrangement, you're just going to take your central atom and basically just do one single bond from the center guy to all the outside atoms. Remember that each line represents 2 electrons. That will use up a certain number of electrons from your total. The remaining electrons should always be put on the outside atoms in pairs of electron dots until all the outside atoms are full with 8 electrons, unless it's hydrogen. And then if you are done filling all the outside atoms and there are still electrons, then they should go to the center atom and be put on the center atom as dots. At that point, once you get to the center atom and you're putting dots on, you should be out of electrons, hopefully, at that point, if you did everything correctly. It's at that point, once you're out of electrons, you want to make sure everybody has met the octet rule. Everybody has 8 around them. If they do not, then you want to actually fix it. And this is really where you want to get into your double bonding. And you want to try to use double bonds to fix it. And if that doesn't fix it, then you should go to triple bond. So as I said earlier, you typically do not want a double bond or triple bond right out of the box. As usual, will not get you the right picture. You want to kind of save that to fix something that went wrong for you. And the way we do that, like I said, is single bonds first. Then we go for all the possible double bond possibilities. And then if still not there, got to go to triple bond to try to fix it. All right, so let's see how that works here together. We want to draw the Lewis structure here for NF3. Nitrogen is group 5 on the periodic table, so it has 5 valence electrons. There are 3 fluorines. Each one is 7 from the periodic table. That is 26 valence electrons. So once again, in my picture, I should have 26 valence electrons in my picture. In this case, between nitrogen and fluorine, I know fluorine is the most electronegative, so that should not be in the middle. Again, it should be the least electronegative. So we should have nitrogen in the middle. We should have fluorine around. And to answer the question somebody might have, it does not matter. You can put the fluorine on top rather than the bottom here. It really doesn't matter where you put it, as long as it's somewhere around there. Now that I have it, I'm going to do what I said before. We're just going to make simply one single bond from the center atom to each of the outside atoms. Each line represents 2 electrons, so that's 2, 4, 6 electrons I just put up there. So I'm going to take 6 off. That's going to leave me 20 more electrons that I need to put on this picture before it's done. They are again going to go on the outside first in pairs until everybody on the outside has 8, unless it's hydrogen. 2, 4, 6. That will fill that guy up. 8, 10, 12. That will fill that one up. 14, 16, 18. That will fill that one up. At this point in my picture, I just threw on there another 18 electrons. That means I have 2 more electrons to go. I have filled up everybody on the outside. Those last 2 go right there in the center as a pair of electrons. So again, outside first, fill it up, work your way to the center if necessary. At this point, we now have a picture that has 26 electrons. The last thing we want to make sure of is, does it meet the octet rule? So 2, 4, 6, and 8 for that fluorine. Really, all the fluorines are the same. 2, 4, 6, 8. 2, 4, 6, 8. Nitrogen, 2, 4, 6, and 8. Everybody has 8 valence electrons. My picture has 26 total electrons. Without all the highlighting there, that would be the correct Lewis structure here for NF3. Question? Okay. So why don't you try one there? Why don't you draw, not that, because that's the one we just did. Why don't you do nitrate there and draw the Lewis structure for it, NO3 minus. The end here. We got 5 for our nitrogen in terms of valence electrons equal to the group number. We have 3 times 6 for the oxygens, which is its group number. This does have a -1, which means it did gain an electron, so we do need to add 1 in there. Otherwise, we're going to be a little short there. 18, 19, 24 electrons here. Again, if we look at the periodic table, nitrogen and oxygen are right next to each other. That means oxygen actually is further to the right in that period, and that would be more electronegative. That means nitrogen should go in the middle. Once again, if you have 1 element and 3 of something else, probably the 1 guy is going in the middle. Again, we're going to do a little oxygen action here. We're going to do a single bond to each of those. So that is 2, 4, 6 electrons, 2 for each of those lines. That gives me 18 more electrons to go. On the outside first, so 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I just put 18 more on, got nothing left. Is everybody good here? The nitrogen is not good, right? Nitrogen has only 6 electrons, so we do need to fix it. So can I just put a couple dots there and call it a day? You should not, because now I have 26 electrons, and that's too many. So this is a situation where we do need to make a double bond to try to fix it. Now, in this particular case, we could erase the nitrogen like that and put it back, hopefully. There we go. There we go. We could make a double bond to fix it. We could actually do it from any of the oxygens here. They're all equivalent to each other. Can I just lay a line in there to do that? I cannot for the same reason, and now 26 electrons. The guy on top now has like 10, and that's not so great either. So when we actually make a double bond, and by the way, when we make a triple bond as well, what we're actually doing is taking a pair of electrons, and we're going to bring it in to make that double bond. And that will get us here something that looks like this, with a double bonded oxygen up on top. Now, because this does have a charge and is an ion, we typically put brackets around it with a charge on the outside. Now, everybody has 8 electrons if you count up the oxygen here, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and nitrogen, 2, 4, 6, and 8. So everybody has 8 electrons. There's still just a total of 24 electrons. Now, you absolutely could have double bonded if you wanted to, say, to the oxygen to the left, and it would end up looking something like this. Have some single bond action there. And you could have double bonded there to the right, or the other side there, left, I guess in this case. And it would look something like this. Doing the same thing, bringing those electrons in to do so. And basically, each of these Lewis structures are related to each other. These are what are known as resonance structures. And resonance structures occur when you have this type of situation where you have basically more than one option where you could do that double bond. And the reason for that is those double bond electrons in this guy, they are essentially just kind of moving around. So at any given point, they're delocalized. It could be at the oxygen on the left, the oxygen up on top, the oxygen to the right. And no one Lewis structure will adequately sort of describe the bonding. So you could draw 3 equivalent structures, which are known as resonance structures. If you were asked a question of draw a Lewis structure for NO3 minus, you could lay up any one of the 3 pictures would be perfectly fine. If you're asked to draw a Lewis structure in all resonance structures, you're supposed to draw all 3 of those structures. Any questions on that there? Okay, so why don't you try some here? Why don't you do SO2? Why don't you do H2S? Why don't you do N2? Do NH4 plus. And let's do CO3 2 minus as well. And so for each of these Lewis structures here, why don't you draw them for next time and have them ready to go? We'll